Hello, everyone. My name is John Twardock, and I have with me Casey Pirano. We're from a company called EMA. We are a technology partner of Ansys. We're the developers of electromagnetic solutions that are marketed and distributed through the Ansys channels. Today, I wanted to walk you through building out an electromagnetic test environment, really to make sure your products are successful. And the flow of things, I'll walk you through a little bit of what's happening. What are the trends in the industry right now, and what is the impact of those, which gives you a feel for why we've really tried to design a solution to address those challenges. Casey will give you a quick demo just to show what the tool looks like, and then we'll also cover a little bit about some of the multiphysics capabilities that are available with electromagnetics. But let's start with a kind of a simple question here. Why do your teams care about electromagnetic compatibility? And that's your product team specifically. They care, frankly, because they have to. It's mandatory. So having EMC compliance is typically, it's required before you can ship your products. And you can see on the right-hand side of this slide a bunch of different standards that are imposed for EMC. And this list continues to grow. So it doesn't really matter what industry you're in. Typically, there will be some level of test standard that you have to meet. And a survey was done of the EMC test equipment and test lab providers. And unfortunately, what they have found, and maybe it's good for them as a business, but about 50% of the companies that come to them fail their EMC test on the first pass. And over a third of them take at least 3 iterations to pass this test. And those of you who are involved in that understand that testing like this, first of all, can be very expensive. It may require a redesign, but it's also really time consuming. And so you really spend a lot more energy and time if you have to go back and retest. And sometimes just scheduling into the lab to get the tests done can be an issue. And what they're seeing is people are doing one of two things. They're either going in with no idea whether or not they will pass that test, or they've really significantly over-designed and still are hoping that that will cause them to pass it. Either way, it's a problem for them. So when you see any compliance test that's being passed at such a low rate, there's a lot of room for improvement here. A study from Frost and Sullivan of the overall market, the trend's only going to continue. So because of the increasing density of electronics due to all the trends that are happening, the demand for electromagnetic compatibility, not only the test equipment, the software to predict it, and test services is growing. And how much? Well, it's compounded annual growth rate of almost 11%. The market was hitting almost $4.5 billion in 2022. So it's a rapid growth. What are the trends that are driving this? Well, I'm sure you can guess quite a few of these. Electrification is one. And electrification is not just electric vehicles. It's the electrification of anything that was previously combustion engine driven, or electrification of things that can be automated. And this really leads to some other things. Autonomy, autonomous and safety systems, with the number of sensors necessary to do autonomous systems. The ESD and EMI environments are getting more complex. Connectivity, we all want to be connected at all times. That's true of just about any industry, and we're all walking around with smartphones and staying connected all the time, but we're expecting that to happen with more and more products as well. The privatization of space, that's a very strong trend, and that really supports some of the things you're seeing above here, the connectivity especially. It's been stated that in the next 5 years, more items will be launched into space than have been launched in the previous history of mankind. And many of those will be launched by entities that are private. So it's not just governments anymore. Space has now become big business. One mentioned before, miniaturization of electronics, getting more power in a smaller space. The density is really increasing, and that trend will obviously continue. And another trend is that supply chains have become somewhat unreliable. So there's been quite a disruption in supply chains, and we'll look at an example of that here. Really an example from the auto industry. So one statement here is looking at how does this impact businesses? Because if you're going to make a case within your company to improve your electromagnetic compatibility capabilities, you're going to need to tie that to some economic benefit for your company. And I have a few interesting examples that show what the impact can be. Here's one from Jim Farley, who was the CEO of Ford this year. When they released the Mustang Mach-E, they recognized there was almost a mile of additional cable and harnessing in there, and really it made the vehicle heavier and also was costing them an extra $300 per battery. And they did that because, well, they were really rushing to get to market and didn't have time to optimize the design. But what that meant for him and the company and the shareholders, they estimated about $2 billion of profit came off the table because of that additional cost. Also, the supply chain issues, and again, the auto industry was hit pretty hard with them in 2023. That outlook really continues, and by that, really, it's caused some of those larger companies to change the way they're looking at their procurement strategies. They couldn't rely on a single vendor, or they've gone out and purchased a vendor who supplies something that's really critical for their products. But either way, now they're looking at plugging and playing many different components from different suppliers, and that creates a lot of uncertainty in your design when you have to swap out components. And we all know what one of the components was that was in short supply, and that was chips, but the other was wiring and wiring harnesses. Those were the two key things that the auto industry struggled to get. And if you're in any type of electronics, you probably experience that as well. Following along with the auto industry trends, the global automotive electronics market is increasing. And that's not only true for automotive, but lots of other products. But as an example, the compounded annual growth rate of that market is almost 9%. It's expected to be almost 470 billion by the end of the decade. Well, what does that mean to you and I? You and I as consumers, we've seen a dramatic cost increase in how much electronics is costing in a vehicle. So back in 1980, they estimated about 10% of the cost of the total car was electronics. 13 years ago, it was a little over a third in 2010, but estimated by the end of the decade that half the cost of a vehicle you buy will be the onboard global or the electronics. So it continues to grow and exacerbates the problem we're talking about. And if you look at an auto here, just this auto example, cars are an extremely complex electromagnetic environment with the number of sensors that are there, safety sensors and speed and steering sensors and automated driver assist sensors. You would couple that with the motors that are in the vehicle, motors for your windows, your wipers, your sunroof. And this picture is not even an electric vehicle. So imagine if it's an electric vehicle and there's a giant battery on the bottom, electric motors driving the wheels, and very large current going through conductors as one accelerates. It's very complex. And in addition, everyone wants to be connected in their car. So you've got multiple frequencies and signals. You've got Bluetooth and radio and GPS and microwave signals going through the vehicle. So at the end of the day, a car has become complex. And every single component there that I mentioned, if you're a supplier in this market, each of the components can either be an emitter or a victim of electromagnetic interference. So it's really becoming critical that you understand the environment that your product is going to be operating in. So to do that, you have to have a very good strategy for managing electromagnetic effects. It's no longer okay to just design overshield and pray when you go to test. And a couple of key questions to consider when you're looking at your strategy at your company. Are you being proactive or are you still reactive? Have you designed electromagnetic compatibility into your process? We would contend that digital simulation of the effects is one way to get it into your process as early as possible. And that was certainly the premise for some of the tools we've developed. In addition, are you being collaborative with this? Electromagnetic compliance is a collaborative effort. It's collaboration between the mechanical and the packaging guys and the electrical and system level design guys. It's also collaboration between the components and the full ecosystem that's being designed. And then you have to correlate simulation and test, right? Simulation by itself without some correlation to test is certainly questionable. You want to raise your confidence by having correlation and validation between the two. This allows you to be more adaptive, so you can adapt quickly and also capture what your best practices are. So these are key things in big buckets to consider as you're looking at your own electromagnetic effects. So a basic premise and a value proposition for any type of simulation is this: the earlier you find a problem in a design, the more valuable that is. And why is that true? Well, it's true because the opposite happens. If it's later in a process and you discover a problem, the more expensive that is going to be to fix. And so that's really why digital simulation lets you get after this before you're actually cutting metal or building prototypes. And we have two solutions designed specifically for that. And on the left side, the Ansys EMC Plus solution is a virtual electromagnetic compatibility platform. It lets you model complex systems for EMI, EMC, E3 effects. You can consider the cables, the harnesses, the shielding, the gaps, all of that. On the right-hand side is the Ansys Charge Plus solution. This is a little more specialized, but it allows you to look at electrostatic discharge events. And it's a very multi-physics solution to let you do that. But I would say this is the arcs and sparks of things in electronics. Both of these have been designed with the idea in mind that you've got to be pretty agile to do this because you're trying to keep up with your design department. Here's a quick look under the hood. I won't go into great detail, but the codes are built specifically on a finite difference time domain solver. Both the Charge and the EMC Plus solution have that. The advantage of that type of solution and that solver is that it uses a voxel mesh, which is very fast and forgiving, both as a solver and as a mesher. We couple that with a multi-conductor transmission line solver, and that's really important to note. When we model something complex like this airplane that you're seeing here, that itself can be a fairly large model. But imagine if you were using finite elements and you mesh the entire aircraft, and then you put maybe 500 cables in it. And the cables can look complex, like something you're seeing here on the left. The mesh for one cable alone would be just overly burdensome and too large. The problem size would explode and be difficult to solve. So we do not model the cables that way. Our cables in these models are represented as three-dimensional line segments, but they are assigned a very complex two-dimensional cross-section like you see here in this image. And that allows us to represent the full cable bundle, the conductors, the insulators. And then that is coupled to an Nexum transient circuit solver. And those three co-simulate to allow us to really model some extremely complex ecosystems for electromagnetic compatibility. And it makes it fairly easy for the user to pull in a CAD geometry and then import or define all of the cabling very quickly and get a solution. On the right-hand side, I won't go into great detail. There's a lot of physics under the hood with the Charge Plus solution. The key thing to note here is in the bottom side, the nonlinear air chemistry. That allows us, allows our customers really to look at the air properties, the temperature, the density, humidity of the air, and consider how that impacts an arc jumping across a gap, for example. And that is a fairly unique capability to do that. The key features, I've kind of touched on these a little bit before, but the ability to pull in a CAD geometry of something fairly complex and get it up and meshed and running very quickly. And the key is that you can maintain pace with the design changes and modify things quickly and keep going. The geometry can be imported as a CAD model very quickly. We've built this on top of the Discovery modeling solution, so it lets you import that geometry and get it meshed very, very quickly. You can also import your cables in standard formats like KBL. The mesh is extremely forgiving, and we hybrid solve. I mentioned the three solvers working together, but most importantly, I think, is that we've validated a lot of this through testing. EMA as a company has been in business almost 45 years, and we've mostly done work in the federal air and defense areas. So we've got lots of references with customers and validations that have been done on extremely complex aircraft and spacecraft. And as those of you who know that industry know how stringent the requirements are there. So we've got lots of validation in that space. I mentioned before looking at the ecosystem. So electromagnetic compatibility, it's a team sport. You have to have your mechanical or your packaging guys working closely with the electrical teams. you really have to also consider the component level simulations and validations you do, along with the ecosystem. I mentioned the components can be emitters or victims of EMI, EMC events. And then finally, you have to also correlate and validate your simulation with testing and vice versa. All of those are things that this really the solution is designed to let you do. So here's one example of a workflow that we've created. If you're a packaging guy and you've been asked to do shielding effectiveness of a design, you may have to do this multiple times as the design evolves. Well, here you can, with a single click, you can import that CAD model, and we'll automatically assign the materials, boundary conditions, and set up a domain and an excitation, mesh it, and then once it is solved, it'll produce for you a statistical view of the shielding effectiveness of your design. So you can very quickly get up to speed and again, monitor this and do it in real time. And here's just a view of that plot showing you at a certain frequency, hey, the shielding effectiveness really starts to drop off. So if a mechanical packaging person wants a tool to just validate that for their design, this is a very easy to use and simple way to do that. And we're working on a number of very easy workflows like this for repetitive tasks that we know people are doing in this space. I'd like to give you a kind of a view now of what the product looks like. You're seeing this here, but I have Casey with me today who can show us a view of the overall interface and what it looks like. So I will stop here, and Casey, if you would, I'll let you share your screen.
Yeah, so I'm just going to give you a quick rundown of what workflow looks like in EMA 3D, as well as kind of what the interface looks like. So on the left here, or in the middle, we have our actual CAD geometry. It really hasn't been cleaned at all. That's not a very important step with the voxel style mesh. Any kind of imperfections will be meshed over when you go to mesh. So you don't have to spend tons of time cleaning CAD. On the upper left is the structure tree, which has all of the different parts of our CAD. And as John mentioned, you can import CAD from something like 50 different types of files. It's a lot. And then underneath that is our simulation tree for EMA 3D specifically. And that kind of goes through what the workflow looks like in order of how you would probably do it. So you would start with setting up the domain, then you would try and set up your harness and move on to sources and definitions, etc. Just to show you kind of what that might look like and how quick it can be, we've tried to make this as easy as possible. So you would just click the big domain button, and then you would set your lowest frequency and highest frequency of interest, so what you're trying to model here, and that will automatically set up your time step and your spatial step, which is shown here. So we're meshing this car at 10 millimeters. So pretty fine resolution. You'll see that it meshes super quickly when we mesh it. But all you really need to do is set up here is your lowest and highest frequencies of interest. And then you just want to make sure that everything is encapsulated in this domain surrounding the car in order to get it to mesh. And then you would assign some kind of excitation to that, which is the second panel up here. That can be anything from a current source to a voltage source. You can do antennas. You can also do a plane wave, which I'm going to show you here. So you would just click plane wave. And we'll click show names here. So you can see, actually, let me turn this a little bit. So there's our plane wave there with our different field vectors. And so we're impacting this from the side, let's say, although we could rotate it if we wanted to, wherever we want to put it. And then it assigns automatically a Gaussian source to this plane wave. So that's based on the lowest and highest frequencies of interest that you set in the domain section. So you don't have to worry about setting any kind of source signal for that. It does it automatically. And then if you want to, which you need to, is assign the materials. So you just click materials, you select something, either an isotropic surface, anisotropic, frequency dependent. We have a bunch of different options here. And my computer is going to auto save right in the middle of this. I apologize. And so you would just go to this menu over here, and you can assign that material any color you want. You can change the permittivity, permeability, and the important one is going to be the electric conductivity. So you can just change that to whatever you want. I don't know, 1.2 E7, let's say. and you would want to name that, let's call it a composite. And then you can do a couple things. You can either assign it piece by piece by clicking on the CAD directly, or if I wanted to, I can go over here to the structure tree and I can select maybe the body, and that will assign that material to the entire body all at once, which is what just happened here. And then once you're done assigning materials, you would want to put in some kind of probes. That can either be a field probe, maybe if you're doing shielding effectiveness, or some kind of emissions, you would put in a field probe, which are very easy to set up. It's very similar to the domain. We also have voltage and current sources, probes, if that's more what you're interested in. And then, as John mentioned, one of the easiest things about EMA 3D is how easy it is to assign cables. So to do that, you would just flip tabs over here to our M harness tab. And under the harness section, we have this cabling button. And you would select what kind of cable you wanted, whether it be an overbraid shield or just a bare conductor. We also have some pre-made cables, such as twisted shielded pairs, that you could do. And so let's just say we want to assign a conductor to something. I'm going to go ahead and hide the body of the car so we can see inside. And we would just select a line inside. Some of these are already set up. And then in our library over here, we actually have a bunch of different wires already populated for you with their cable properties provided from our testing. And so you can expand general, you can look at the area, the radius, the resistance of it. You can change all of that, the jacket dielectric, anything you want. And then you would just click the green check mark. And then if you wanted to see what your cable cross section looks like, you can inspect that cross section using this button. You just hover over these different lines where you've already assigned cables, and you can see that some of them are as simple as one conductor, and some of them are more complicated with a twisted shielded triple, twisted shielded pair, and a bare conductor in this one. And again, those are all represented in just that single line without actually having to mesh that whole line or trying to mesh each individual component. And then what you do is you would just click mesh, which I'm going to do live here. It should take about 20 seconds, I think. But as John mentioned, voxel style mesh is very forgiving. It's very fast. It doesn't take a lot of CAD cleanup to get it going. So now it's just going to show me my mesh here. It has finished meshing. Of course, it's going to get stuck on this part. Okay, so that wasn't too bad in the end. So you see we meshed our entire car, all of the components and everything at 10 millimeters. And then the only thing left to do is to actually run it. So we would click the big start button here, and that will come up with a pre-processing window where it will give you any warnings that you need to know about before you run this. So maybe you assigned a pin voltage source, but you forgot to actually assign it a source or a signal. So it will warn you that you need to apply that signal before you run it. So you can go back and do that so you don't waste your time running something that's not going to work. And then you would just click run here. And it's generally pretty quick. We've done large airplane models that run in 12 hours or less, and those are entire airplanes full of cable harnesses and everything. And speaking of those, we actually have a built-in help section here, this button here, that has pretty much everything you need to know about EMA 3D cable, or EMC Plus as it's called now. We have all of the technical notes. We have the capabilities section that really gets into the nitty-gritty of all of the FTTD, the transmission line solver, any kind of buttons that we have in here. It explains them all in great depth. The guy who made our solvers did a great job at that. We also go through the graphical user interface, and we go through button by button basically and tell you everything you need to know about creating the domain, the time steps, the lattice steps, what your boundary conditions should be, and what the background you might want. And we go through that for every single button. We also have a whole section on tutorials. So EMA 3D cable right now, or EMC Plus, has about 20 built-in tutorials, and about half of these also include videos of us walking you through those tutorials if you want to follow along. But in general, it's a really step-by-step kind of a how to do any of these problems you might want to. So you might want to do a DL160 lightning strike. You might want to do a transfer function. This walks you through how to do our Nexum cable terminations. If you have kind of an RLC circuit, it tells you how to put that in there. And I think with that, that is pretty much the basics of the software. We really tried to set it up to be user-friendly. We know that there's some way less user-friendly ones out there, and we just set it up so that you can go right down the line here, domain, harness, excitation, signals, etc., and kind of follow along so that by the end, you know you've set up the simulation with all the necessary components.
All right, Casey, so are you, should we hand it back over to John now?
Yeah, Casey, are you able to just show the overlay menu very quickly?
Oh, yes, I'm sorry. I forgot the overlay. Yep. So if on any of these buttons, you can do, let's see, let's pick the current source maybe. If we hit F1, it pops up with an explanation of what that tool is. It tells you what each of the components over here in the properties panel are. And it also gives you brief instructions on how to use those tools. And then there's a short video that shows you how to use the tool as well. And that actually reminded me, let me get out of the overlay help menu, and that's available for all of our tools right now, is we also have, if I minimize this, once we run this, we get our results populated in the simulation tree, and then we can post-process right here in EMA 3D. We can do shielding effectiveness, we can do transfer functions, we can just plot, this one is an example of cable crosstalk. I electrified one of the cables, but not another one. And this is what that's showing. This is showing the victim current induced by that nearby excited cable. And then these planes here were set up to capture animations, which I have here. So for instance, this is if you're looking down at the car, this is showing that we have excited some of our cables here, and it's showing the current passing along those paths of the wires, but it's also showing all of the induced current on the rest of the car. So you can actually see the car body because current is being induced on that, which you might or might not want. Additionally, this is what it looks like for a plane wave. This needs to, so you can see what you would see if this started over was you would see the plane wave coming in, it would impact the windshield, and you would actually see it pass right through the windshield, but it would not be passing through the car body because that's steel. And then it would bounce around in here and kind of get the pattern that you're looking at here, which is also capturing the E field generated from those excited cables that I showed you earlier. So this will be more interesting in about 10 seconds when it restarts here. Here we go. So you can see we have our plane wave, it comes in, it's avoiding the car because of the steel, but then it hits the windshield and goes inside the car and kind of fans out from there. So this is something you can do right in EMA 3D, and you can output it as a GIF, which is what I've done here. So we've really tried to keep everything you need to do inside of the software, so you don't really have to use Python unless you really want to or something like that to post-process your results. Thanks, John.
A complete simulation, lightning strike simulation for an aircraft. And the situation here was this was a customer of ours. We do quite a bit of services in this area, and we had done a consulting project with them years ago when the plane was originally built. Now it's a dozen or so years later, and of course they're going to upgrade a lot of the electronics in that aircraft. And so in order to do that, they have to get the entire aircraft recertified. So the challenge was to try and get this certified with simulation. The testing is extremely expensive per test, and they wanted to avoid this if at all possible. So for us, this was really one of the largest models we've done. There were 600 different cable types, meaning cable cross sections with over 1,600 cable segments in it. Just a very immense model. And the results, we ran 24 lightning scenarios in about 90 days for them. Had many probes in the model, but at the end of the day, this has now been submitted for certification. We had great correlation to their test results, and we're expecting FAA approval of this model. So this is just to give you an idea of the magnitude. You can see here all of these line segments represent cables in that model, and you can see this cross section how complex some of the cabling certainly can be here. Another example, we've got our friends at Intel. They were using finite element methods to look at some of the components of their servers, but they also started to realize that, hey, the cabling here is really impacting a lot. There's a lot of coupling going on. So they wanted to model all the cabling, and as you can imagine, in racks of servers, there's quite a bit of cabling. So they wanted to model this, but it was just taking them, they tried to do it with the finite element method alone, and it became overly burdensome and ridiculously large. So they said, we'd really like and they were using at the time the HFSS and SI wave tools, but they said, we'd really like this to have a strong link over to the EMA tools. And so I give them credit. They got us to sit down and actually build out this integration. The net effect of this is that we were able to satisfy what they wanted. We were able to import the detailed high fidelity models that they had inside the server from HFSS and SI wave and pull that in and then run simulations. So they didn't think this was possible. They were extremely happy. We've got a very nice testimonial from them saying, hey, we didn't think it was possible. And now because Ansys EMA sat down and came up with this workflow, it was great for all of us. And you can just get an idea here. Here's just a view of the radiated emissions, both inside and outside of the box. This printed circuit board, that emission was imported from a result that they had done with the Maxwell tools or the HFSS tools. So we imported a bunch of the components and carried forward with a full system level view, including all the cables and harnesses in this model. I do want to mention a little bit about our ESD applications. Just for those of you who have any concerns for ESD, I'll just quickly show you some of the types of applications that it can do. This is a broad list of what types of applications we see it being used for. We're seeing a large growth in some of the high voltage power systems out there, arcing in those, and high voltage switches and breakers. We can do dielectric breakdown. We've seen a lot of solar panel work with that, but dielectric breakdown happens in many other applications. And then lightning attachment modeling, and certainly anybody who has to do ESD testing or non-contact ESD gun testing. We can do that. So this is just one example. Again, using an automotive example, I'm putting a conductor in here. Is it going to be too close to the chassis? Is there any problem? And the simulation, and I'll let it run for a second here. You can see as the charge builds up, eventually, it's been determined that yes, an arc will actually jump across that gap. I'll let it develop a little bit so that it does. Takes quite a few time steps to get there, but you'll eventually see it flash over as it builds up. And so this type of simulation was possible. You could do this with multiple conductors here. In this case, they were just really looking at, hey, if I route something close to the chassis, will I have a potential problem? And these can be very expensive to mitigate if you have them later. Here's another example, a lightning attachment. We can determine where lightning will attach. In this case, we're doing it with an aircraft. And you can see as the charge builds up, eventually it will attach. And where does it attach? And then really the key here is to determine whether the rest of your electronics can survive that. And that simulation is something that we can do on even small components, ground equipment, and it's becoming more popular with any communications equipment, and certainly now with electric vehicles, there's concern about lightning attachment as well. With large or power line, this is an example of if a power line is running past maybe something else. In this case, it's a tree. This is something that the power industry is quite concerned about because, as you know, forest fires have been running pretty wild all around the planet. And many times the regional power provider is being blamed for this, for not keeping their lines away from. So this is an example of a simulation that can show that, that at what point will that floating conductor be too close to the tree, and what point will an arc occur, which could then obviously spark a forest fire, which is unfortunately huge liability for those involved. So it is a problem, but we see this in other areas too. It can be in electric trains, for example. We're doing some work with power companies where their workers are going up to high tension lines and working on them, and they're experiencing some unwanted arcing there as well, which is a very dangerous situation for the workers. So the ability to watch this jump across an air gap is really the key to this ESD solution. Another application, just arcing in high voltage systems here, you get a view in this case of switches and breakers, and will an arc form across these two? And in this case, it actually did, but just gives you a view of what can be done. Another example is ESD gun testing, which is a lot of products have to do this test, and so you want to again validate that test versus lab results. And in this case, you can do that. So this is again, this type of simulation previously wasn't really available to do, but you have your input. You do need to understand the air properties you're working with because it matters greatly. And we've seen some modeling where additional things like salt brine has caused a change in conductivity and made an arc possible where they didn't think it would be possible. So it depends very greatly on the environment that you're doing this in. But this is another type of simulation that's available. And then one last comment here, we've integrated the electromagnetic solutions that we have with a lot of other Ansys physics to come up with some extremely unique solutions. And this is again an example in SI Wave. Here's a full PC board model. I mentioned before you could export that, and we'll import that and use the output of that as part of a model that we're doing, for example, for radiated emissions. And now there's the full PC board inside of the model. And you've seen this animation before, but here is the radiated emissions with that PC board inside of it. That's just an example of a workflow that you can do. Similarly, if you've got antenna models, HFSS, if you've got an extremely high fidelity antenna model, and then you want to look at a full vehicle simulation, you can absolutely do that. So we will take the results from HFSS, import it into our model, and carry forward with that now, with that antenna in a full system model here. And just showing you some of the post-processing of the electric fields and the animations of that. Or coupling to a cable, for example, if these emissions are coupling to any of the cables, here's just a view of voltage probe of that and what happens when that occurs. We've done a couple of really unique solutions. There's an Ansys Rocky product, which is a particle physics solution. It allows people to predict how charged particles will deposit on a surface, or how charged particles that have a velocity or passing over a surface will invoke a charge and potentially arc with the surface. And so this is called triboelectric effects. We developed a solution for the picture you see here, which is a moon rover. It's basically an electric vehicle that's operating in a very dusty environment, which would certainly define the surface of the moon. And there was concern over that developing a charged environment, or the dust accumulating on the solar panels and rendering them very ineffective. Another integration is our coupling with the Fluent and CFD. We can predict when an arc will occur, but the next question is, well, then how does the arc propagate due to the superheating in the local area? And so that is now a coupled solution between our ESD solution and also the Fluent solution. This has also led us to do some semiconductor plasma modeling. That could be an entirely different discussion, but we do have now capability to do that, to look at plasma enhanced chemical vapor deposition process for semiconductors. If you're familiar with OptiSlang, it is really a great solution for setting up and running optimizations. This is just a simple example of running hundreds of simulations to look at the parameters and really look at the best configuration of cabling. So we've got people using it for cabling design itself, trying to minimize some of the crosstalk between cables as well. So you can set up these parameters and run them and come up with ultimate configurations or optimal configurations. If you're in the space business or you're running missions, we also have integrated with what's called the AGI SDK space solution, so we can take into account environmental effects for items that are in space, like this satellite. We import those conditions from their space environmental effects toolkit, and then we can mitigate any harmful ESD effects and simulate those based on that mission profile. So just a lot of physics under the hood here. Where are we going in the future? We've worked on and we'll be releasing in an upcoming release just specific absorption rates. So what happens when the human body is actually subjected to so many different emissions like this? What does that do? And what are the absorption rates? And certainly, as you put yourself into a more and more complex and intense electromagnetic environment, everybody wants to know what's happening there. So we are working on solutions like that for the future as well. And I think the electric vehicle industry is kind of all over this, because everybody gets in there, and there are reports that some people feel they're getting ill from being inside the vehicle, but they don't know why. So to wrap things up, I'll just leave you with three things to think about. First, I mentioned it early, complex environments are going to require a really robust strategy. So I recommend that you consider being much more proactive and simulate not only the components, but look at the entire ecosystem, because your component or even your design may have to operate in a very complex environment. And as we all know, it's expensive to fail, and it can actually impact safety and liability for your products. We've developed some very new methods that are really targeted at this, at helping to mitigate this. So to achieve that, you really want to look at system level EMC and where your products are going to operate. And ultimately, we're trying to reduce having to go to test so often and having to fail test so often. Ideally, we'd love customers to go in and pass a very high percentage of the time on their very first try. If they don't pass, we can mitigate the problem with simulation. But also be confident that when you go in, you've got a very robust design and you have not over-designed. And I think over-design, with the example I showed with Ford, a very expensive thing to do if you're continuing to over-design. And then finally, it's possible. I showed you some examples of some very large models. The efficiency of the solvers is there, the compute power is there, the ability to pull in an entire CAD geometry and very quickly look at the overall electromagnetic design. That is now possible to do. So I'd like to, at this point, open up if there's any questions. We'd certainly like to address them there, and I'll turn it back over to you, Conrad.
Great. Yeah, we have a couple of questions here. So first one is, what are I think he's looking for like kind of the more minimum or base computer requirements to run EMA solutions. And then like when you guys were talking about the 12 hours for the whole airplane simulation, what kind of a computer system was that, if you guys have that on hand?
Yep. I'll let Casey address those, because I think he's actually run some of that.
Yeah, so the biggest thing is a dedicated graphics card, one of the newer ones. That's really important for setting up the model because Discovery requires it. You can run these on a laptop. A lot of people at our office do. I have a couple $1,000 desktop that I can run it on. The 12 hours for the airplane, that I think was running on 72 cores, so 72 processors. So that was actually quite a big computer. So you could expect that it would take a little longer if you didn't have that many cores available. But if you get a 20 core computer that has fast processors, you could probably match that time. This 72 core one actually has pretty old processors, so that slowed it down somewhat. But so it just kind of depends on what your use case is, how big your models are going to be, how complex everything with the harnesses are. But in general, the setup that you need is actually not that expensive. It can get expensive if you really want to speed up the simulation time, but to just get started, it's actually, you could do it on almost any new laptop.
Great,
We
perfect.
have actual specs that we could send out, as well as to what we recommend. I don't have them on hand right now, but we do have them.
Great. Looks like we have another one here. Is it, and I think you guys answered this one, but we might just want to pull it back in. Is it capable to do surface charge simulation for space applications like on-orbit surface charge distribution?
The short answer is yes. And if you can get your mission profile, if you have a mission modeling solution and you can get the environmental effects across the entire mission, we can certainly correlate those as well and give you the portion of the mission where you're at most risk.
Okay, great. A couple here quickly here. And I believe Casey's presentation or demo showed this, but we have a user that uses the electronics desktop Ansys tools already. And they're just wondering, like, what's the learning curve to use EMA 3D? And how long would it take them to get up and running to do some basic cable modeling?
Boy, yeah, go ahead.
Go ahead.
Since you do a lot of the training, Case, please.
Sure. Yeah, so I actually wrote all the documentation for the training. We have 2 courses. We have an introductory course, which you can probably complete in 10 hours. And we have an advanced course that takes maybe just a hair longer. The simulation time on those is a little bit longer. But I would say by the end of the introduction course, you're well on your way. And by the end of the advanced course, you can pretty much do everything that we have to offer currently. So it is, I think, very easy to use. And the tutorials kind of we have a very wide array of applications in the tutorials. So there's a good chance whatever you're trying to do, we have a tutorial that covers it. So I think that the spin up time is pretty minimal for that.
So basically a couple of days to get up and running if you split that up. It sounds like
yeah, exactly.
2 5-hour sessions or something.
That's right.
To get going and get your model set up and everything. And it does look pretty straightforward from what you showed us. So thank you for that. And then, like, what situations would you choose EMA over, like, say Maxwell or HFSS or SI Wave? If we have a couple of examples, like why you would choose this tool over or supplement with this tool in relation to HFSS and some of the other Ansys electronics product.
Yeah, I kind of touched on it. Actually, my first bullet touches on that a bit. It's usually people are using HFSS and SI Wave are doing really high fidelity models of a component. When you want to insert that component into a larger ecosystem, or you want to consider some of the harnesses and cabling coming into it, then the model becomes pretty complex. And to do those type of models with finite elements are difficult to do. So if you want to model, for example, your component in an entire chassis, look at some cabling coming in and out of the chassis, maybe be concerned about descents or coupling to the cables, you'd really want to move to a solution that lets you do that. I think that's probably if you start to get to the point where you're pushing the ceiling of what you want to model, or you're thinking it's not even possible, and we run into this quite a bit where people are like, oh, it's just not going to be possible to model the whole thing. It is. You just have to adopt a slightly different technology strategy to do that. And the good news is if you've got those models already, we can leverage the results and import them very quickly and carry on. And again, Intel really put us in a room and made us put that workflow together so that it worked robustly. But you're not losing anything in the investment you've already done if you've got those detailed models.
Right. So would it be safe just to bring it down to a simple level? Is this is more, if you're looking at the whole system, this is more of a system level analysis versus the individual parts.
Yes,
it's more effective for that.
Yeah, and I think once you get beyond a cable or two, it's really difficult to do that with finite elements if you've got other components in there. And that model blows up.
That's what some of our other electronics engineers here on our consulting side have said, that you kind of use them in tandem, and it sounds like what I've heard from other users. So great. We don't have any other questions here, but